Welcome back to Basic Mathematics. Differential, calculus. Derived function, by first principle, or derivative. In this video, we will learn here definitions and rules of derived function. We define derivative f dash of x to the power of n equals d dx of x to the power of n equals n times x to the power of n minus 1. Note: d dx of k constant equals 0 is called the constant rule. Also, we will discuss the common constant rule, the plus-minus rule. d dx of u times v, the product rule. d dx of u divided by v, the quotient rule, and, in the end, dy dx equals dy dt times dt dx, the chain rule. Derived function. Derived function, or derivative, is defined as the instantaneous rate of change. Derived function is defined as a tool to quantify the change in a function of a variable, say x, with respect to its input variable x at a certain value of the variable x. Derived function is defined as it is the slope of the tangent line at that point on the graph of the function. Derived function. Derived function, or derivative, is defined as the ratio of the instantaneous change in the dependent variable to that of the independent variable. The process of finding a derivative is called differentiation. Line and slope. The equation of a line in slope-intercept form is y equals mx plus c. Note: as x increases, y also increases. Increase in x is directly proportional to the increase in y. Increase in y is divided by with respect to correspondingly increase in x equals m, the slope. The equation of a line in slope-intercept form is y equals mx plus c. Note here, m is the slope or the gradient. Now we defines it as derived function of y, which can be denoted and pronounced as dy dx equals m. The equation of a line y equals mx plus c is a linear equation. Hence, the derived function is constant, which means the slope m is constant. at all point x, y of the line. Graph and slope. Here we draw a graph distance versus time of a train movement. Practically, when we plot a graph of two variables, we can generate some important information from the slope at a point on the graph curve. Graph and slope. Here we have a graph distance versus time of a train movement. We will explore here on the data of a train movement from, say, London to Oxford, which is 100 kilometers away, and train takes 2 hours to cover the distance. As the train takes 2 hours to cover the distance of 100 kilometers, the speed of the train is calculated as 100 divided by 2 equals 50 kilometers per hour. Speed from the slope. Here we have a graph distance versus time of a train movement. Choose 2 points P and Q on the graph at x-axis at 30 and 90 minutes. Read the y-coordinates, distance, of P and Q. Those are 25 and 75 kilometers. Slope equals difference in y, that is 75 minus 25, divided by difference in x, that is 90 minus 30. Speed equals 50 divided by 60 equals 0.833 kilometers per minute, or 50 kilometers per hour. Graphs and the slope. Here we have a graph of distance versus time of a train movement. This was a very simple case, as we used only 2 points, start and finish, and plotted the data. 2 points gives straight line, and speed here is the average speed of the train between 2 stations. We know the train speed varies from start to the finish. Now, we will explore the train movement at every 10 minutes, following the milestone placed alongside of the tracks. Graph and slope. Distance covered is noted at every 10 minutes and plotted on the graph. Though the train covered 100 kilometers in 120 minutes, but the average speed at each interval of 10 minutes is different. Let's check the speed of the train in first 10 minutes. From start, train moved only 5 kilometers. Slope equals difference in y 5 minus 0, that is 5 kilometers. Difference in x 10 minus 0, that is 10 minutes. Therefore speed equals 5 divided by 10 equals 0.5 kilometers per minute, or 30 kilometers per hour. The average speed in every 10 minutes is noted here in the table. The average speed in every 10-minute is noted and plotted on the graph. See red line here along with the distance versus time. See blue curved line on the graph. In first case, average speed of 50 km per hour is plotted by dotted line. The slope of the distance versus time gives us the speed, and the slope of the speed versus time will give us the acceleration. In first case, the speed was constant. It means no acceleration. The slope of the distance versus time gives us the speed, and the slope of the speed versus time will give us the acceleration. In first case, the speed was constant. It means no acceleration. But in second case, we saw variation in the speed with both positive acceleration and negative acceleration. The acceleration can be calculated by rate of the change in velocity versus time. That is the slope of the graph of velocity versus time at any point of time. The slope formula. Before we move further, we recollect our knowledge of slope formula from the coordinate geometry. The slope of the point A, x1, y1, from the point B, x2, y2. The slope m of the point A from point B is defined as height is divided by distance equals AC divided by BC. The slope m equals AC divided by BC equals y1 minus y2 divided by x1 minus x2 equals difference between y coordinates divided by difference of x coordinates. Here, we also recollect our knowledge of trigonometrical ratios of sine, cosine, and tangent. As you know, in a right-angled triangle, there are three sides. Longest side is hypotenuse, and other two sides are adjacent and opposite. So, sine of an angle A equals opposite divided by hypotenuse. Cosine of an angle A equals adjacent divided by hypotenuse. And tangent of an angle A equals opposite divided by adjacent. Remember, tangent of an angle 0 equals 0, slope of the line parallel to x-axis, tangent of an angle 45 degree equals 1. Tangent of an angle 90 degrees equals infinity. Slope of the line parallel to y-axis. Let's take one line of equation y equals 2x plus 5 and calculate the slope of the line between 2 points on the line. At x equals 0, y equals 5, and at x equals 10, y equals 25. Increase in y, 25 minus 5. That is 20 divided by. Increase in x, 10 minus 0. That is 10. So the slope m equals tan equals 20 divided by 10 equals 2. Slope on curved line. Slope of a point on a curved line is not same that of at all points of the curve. Unlike a straight line, to find the slope, we draw a tangent line between 2 points on the curve. Take a simple curve of equation y equals x squared. It is a quadratic equation. We draw it on the graph sheet with its 6 point 1, 1, 2, 4, 3, 9, 4, 16, 5, 25, 6, 36. Slope of the curve y equals x squared at any point is the slope of the tangent drawn at that point on the curve, which gives the instantaneous rate of change of y equals x squared at the point x, y. Note on the graph of y equals x squared, the slope of the tangent at 2, 4 is quite different to that of the tangent at 5, 25. Note on the graph of y equals x squared, the slope of the tangent at 2, 4 is quite different to that of the tangent at 5, 25. Note it on the graph. The scale of x and that of y is not same, so it will not show correct slope at 2 points. For correct slope, we have to calculate from the coordinates or find the derived function of the equation y equals x squared. For correct slope, we have to find the derived function of the equation y equals x squared. The derivative we will discuss little later in detail. Let's first we explore the slope from coordinate geometry on the graph by selecting a point near the point of our attention or interest. To find the slope at the point 2, 4, we take next point 3, 9 on the curve y equals x squared. Increase in y, 9 minus 4, that is 5 divided by. Increase in x, 3 minus 2, that is 1. Slope m equals tan theta equals 5 divided by 1 equals 5. We explore it further by selecting another point closer to the point 2, 4. Redraw the curve y equals x squared at the interval of 0.5 and choose the point 2.5, 6.25 next to 2, 4. Increase in y, 6.25 minus 4, that is 2.25 divided by. Increase in x, 2.5 minus 2, that is 0.5. Slope m equals 2.25 divided by 0.5 equals 4.5. We explore it further by selecting another closer point. Redraw the curve y equals x squared at the interval of 0.25 and choose the point 2.25, 5.06. Next to 2, 4. Increase in y, 5.06 minus 4, that is 1.0625 divided by. Increase in x, 2.25 minus 2, that is 0.25. Slope m equals 1.0625 divided by 0.25 equals 4.25. We explore it further by selecting even closer point. Redraw the curve y equals x squared at the interval of 0.1 and choose the point 2.1, 4.41. Next to 2, 4. Increase in y, 4.41 minus 4, that is 0.41 divided by. Increase in x, 2.1 minus 2, that is 0.1. Slope m equals 0.41 divided by 0.1 equals 4.1. It is close to actual slope. Let's find out by selecting a point even closer. Redraw the curve y equals x squared at the interval of 0.02 and choose the point 2.02, 4.0804. Next to 2, 4. Increase in y, 4.0804 minus 4, that is 0.0804 divided by. Increase in x, 2.02 minus 2, that is 0.02. Slope equals 0.0804 divided by 0.02 is equal to 4.02. Note: the slope is different in all cases, and it depends on how close is the next point. Let's recollect the secant from the geometry of the circle. An intersecting line at two different points of the circle is known as the secant of a circle. The secant is the extension of the chord going outside the circle. Let's recollect the tangent from the geometry of the circle. A straight line that touches the circle or intersects the circle only at one point of the circumference is called the tangent of the circle. The tangent of a circle never enters the inside the circle. The difference between a tangent and a secant is that the tangent touches or intersects the circle only at one point and never enters the inside the circle, while the secant passes through the circle and intersect the circle at 2 points. Slope of the secant. The slope is changing, and it depends on how far is the next point. In this method of coordinate geometry by 2 points, we are getting the slope of the secant of the curve passing through those 2 points, and not the slope of the tangent at the particular point of interest. Now we move to derived function. The derived function to calculate the slope at a point P, X, Y. Let's take the next point Q at a very small interval of h. The point Q's coordinates are x plus h and y plus k. Note the value of k comes from the curve equation y equals x squared. That k is the increment in y equals x plus h whole squared minus x squared. Therefore increase in y equals k equals x plus h whole squared minus x squared equals x squared plus 2xh plus h squared minus x squared equals 2xh plus h squared. An increase in x equals h. Therefore slope at x, y equals k divided by h. Therefore slope at x, y equals k divided by h equals 2xh plus h squared divided by h equals 2x plus h. Considering h is very small and approaching to 0, or h0, bringing 2 points to 1. Hence, h can be ignored and slope is 2x. Here, the slope m is denoted as dy dx, derived function or derivative of y. The slope of y equals x squared. Dy dx equals 2x. To find the slope at the point 2, 4 on the curve y equals x squared, the derived function of the equation dy dx equals 2x, or slope m equals 4 at 2, 4. By this method, we are converging 2 points to 1 by approaching h to 0. In turn, we convert the secant into the tangent. We reached to the basic definition of the derived function, or the derivative. That is the instantaneous rate of change in a function of a variable x, f(x), with respect to its input variable x at a certain value of the variable x. For a continuous function y equals f(x), we deduced that the instantaneous rate of change at a point P, x, y is given by function f of x plus h minus function f of x whole divided by h, where h is taken very small, or can say h approaches or h tends to 0. Delta method and slope. This algebraic method of adding a small quantity h to calculate the slope of the tangent is known as delta method. The derived function, or the derivative, is referred as by first principle, or for function of a variable y equals function of x, or f dash of x equals dy dx equals limit h tends to 0 function f of x plus h minus function f of x whole divided by h. The derivative. By first principle. Now we will apply delta method to explore various functions of x, or f(x), using algebraic method of adding a small quantity h to x coordinate and k to y coordinate. F dash of x equals dy dx equals limit h tends to 0. Function f of x plus h minus function f of x whole divided by h. Let's take a constant function f x equals y equals c. As there is no variable x, so there is no change in y, or k equals 0, or function f of x plus h minus function f of x equals 0, therefore dy dx equals 0. Derivative of a linear equation. Let's take a simple linear function f(x) equals y equals 2x plus 5. First evaluate function of x plus h minus function f of x. That is 2x plus h plus 5 minus 2x plus 5 equals 2 times plus 2h plus 5 minus 2x minus 5 equals 2h. F dash of x equals dy dx equals function of x plus h minus function f of x whole divided by h equals 2h divided by h equals 2. Verify it by selecting 2 points 0, 5, and 10, 25 on the graph. Slope equals increase in y, 25 minus 5, that is, equals 20 divided by increase in x, 10 minus 0, that is, equals 10, equals 2. Slope is same as derivative. Comparing it with the gradient of a line y equals mx plus c, that is m. Derivative by first principle. Let's take a simple quadratic function f x equals y equals x squared. Start by first evaluating function of x plus h minus function f of x. That is, x plus h squared minus x squared equals x squared plus 2xh plus h squared minus x squared equals h times 2x plus h. F dash of x equals dy dx equals limit h tends to 0, function of x plus h minus function f of x whole divided by h equals limit h tends to 0, h times 2x plus h divided by h equals limit h tends to 0, 2x plus h not equals 0. The limit of the gradient as h tends to 0 is 2x. Therefore derivative equals 2x. Derivative by first principle. Let's take simple quadratic function f x equals y equals x squared. Start by first evaluating function of x plus h minus function f of x. That is, a x plus h squared minus a x squared equals a x squared plus 2xh plus h squared minus a x squared equals a times h times 2x plus h. F dash of x equals dy dx equals limit h tends to 0, function of x plus h minus function f of x whole divided by h equals limit h tends to 0, a times h times 2x plus h divided by h equals limit h tends to 0, a times 2x plus h not equal to 0. The limit of the gradient as h tends to 0 is 2x. Therefore derivative dy dx equals 2ax. Note here f dashed ax squared equals a times f dashed x squared. Derivative by first principle. Please note, we have learned so far as 1. For a constant function f of x equals y equals c. Derivative equals dy dx equals 0. 2. For a constant function f of x equals y equals mx. Derivative equals dy dx equals m. 3. For a constant function f, x equals y equals ax squared. Derivative equals d dx ax squared equals 2 times ax. For derivative equals d dx x squared equals a times d dx x squared equals a times 2x equals 2ax. Derivative. By first principle. To understand, we find the derivative of the function f of x equals y equals ax squared plus bx plus c. Start by first evaluating function of x plus h minus function f of x. That is a times x plus h squared plus b x plus h plus c minus ax squared plus bx plus c equals a times x squared plus 2xh plus h squared plus b x plus h plus c minus ax squared minus bx minus c equals a times h times 2x plus h plus b times h. F dash of x equals dy dx equals limit h tends to 0, function of x plus h minus function f of x whole divided by h equals limit h tends to 0, a times h times 2x plus h plus b times h divided by h equals limit h tends to 0, a times 2x plus h plus b, h not equals 0. The limit of the gradient as h tends to 0 is a times x plus b. Therefore derivative equals dy dx equals ax plus b. Sum of derivatives. The function of x equals y equals ax squared plus bx. There are two terms here. To calculate the derivative of the function, we can divide the function in two parts, as there are two terms in the function, and find the derivative of each term. Let u of x equals ax squared and v of x equals bx. Note both u and v are function of x, and f of x equals u of x plus v of x. We solve derivative of u and v separately as du dx equals d dx ax squared equals 2x and dv dx equals d dx bx equals b. Adding the two, du dx plus dv dx equals 2ax plus b. The result is same as f dash of x equals dy dx equals d dx ax squared plus bx equals 2ax plus b. Therefore d dx u plus v equals du dx plus dv dx. The function f x equals y equals ax squared plus bx. There are two terms here. Let the function u of x equals ax squared and he function v of x equals bx. Note both u and v are function of x, and function f of x equals function u of x plus function v of x. We solve the derivative of u and v separately as du dx equals d dx ax squared equals 2 times ax and dv dx equals d dx bx equals b. Adding the two, du dx plus dv dx equals 2ax plus b. The result is same as f dash of x equals dy dx equals d dx. Ax squared plus bx equals 2 times ax plus b. Therefore, d dxu plus v equals du dx plus dv dx. Please note, plus rule. If y equals u of x plus v of x, then dy dx equals d dxu plus v equals du dx plus dv dx. More derivatives. By first principle, let's take a simple cubic function f(x) equals y equals x cubed. Start by first evaluating function of x plus h minus function f of x, that is, x plus h cubed minus x cubed equals x plus h times x squared plus 2xh plus h squared minus x cubed equals x cubed plus 3x squared h plus 3xh squared plus h cubed minus x cubed equals h times 3x squared plus 3xh plus h squared. F dash of x equals dy dx equals limit h tends to 0, function of x plus h minus function f of x whole divided by h equals limit h tends to 0, h times 3x squared plus 3xh plus h squared divided by h equals limit h tends to 0, 3x squared plus 3xh plus h squared. Note h is not equals 0. The limit of the gradient as h tends to 0 is 3x squared. Therefore derivative f dashed x cubed equals d dx x cubed equals 3 times x squared. Derivative of x to the power of 4. Let's take another function f(x) equals y equals x to the power of 4. Start by first evaluating function of x plus h minus function f of x, that is, x plus h to the power of 4 minus x to the power of 4 equals x to the power of 4 plus 4x cubed h plus 6x squared h squared plus 4xh cubed plus h to the power of 4 minus x to the power of 4 equals h times 4x cubed plus 6x squared h plus 4xh squared plus h cubed. F dash of x equals dy dx equals limit h tends to 0, function of x plus h minus function f of x whole divided by h equals limit h tends to 0, h times 4x cubed plus 6x squared h plus 4xh squared plus h cubed divided by h equals limit h tends to 0, 4x cubed plus 6x squared h plus 4xh squared plus h cubed. Note h is not equals 0. The limit of the gradient as h tends to 0 is 4x cubed. Terms containing h will be equals 0. Therefore derivative f dashed x to the power of 4 equals d dx x to the power of 4 equals 4x cubed. Derivative of x to the power of 5. Let's take another function f(x) equals y equals x to the power of 5. Start by first evaluating function of x plus h minus function f of x, that is, x plus h to the power of 5 minus x to the power of 5 equals x to the power of 5 plus 5x to the power of 4h plus 10x cubed times h squared plus 10x squared times h cubed plus 5x times h to the power of 4 plus h5 minus x to the power of 5 equals h times 5x to the power of 4 plus 10x cubed times h plus 10x squared times h squared plus 5x times h cubed plus h to the power of 4. F dash of x equals dy dx equals limit h tends to 0, function of x plus h minus function f of x whole divided by h equals limit h tends to 0, h times 5x to the power of 4 plus 10x cubed times h plus 10x squared times h squared plus 5x times h cubed plus h to the power of 4 divided by h equals limit h tends to 0, 5 x to the power of 4 plus 10 x cubed h plus 10x squared h squared plus 5x h cubed plus h to the power of 4. Note here, h is not equals 0. The limit of the gradient, as h tends to 0, is 5x to the power of 4. Terms containing h will be equals 0. Therefore, derivative f dashed x to the power of 5 equals d dx x to the power of 5 equals 5 times x to the power of 4. Derivative of x to the power of n for the function f of x equals y equals x to the power of n. Start by first evaluating function of x plus h minus function f of x, that is, x plus h to the power of n minus x to the power of n. Remember, x plus h to the power of n equals x to the power of n plus n times x to the power of n minus 1, h plus 1/2 n times n minus 1 times x to the power of n minus 2, h squared plus n xh to the power of n minus 1 plus h to the power of n. Therefore x plus h to the power of n minus x to the power of n equals x to the power of n plus nx to the power of n minus 1h plus 1/2 n times n1 x to the power of n minus 2h squared plus nxh to the power of n minus 1 plus h to the power of n minus x to the power of n. F dash of x equals dy dx equals limit h tends to 0, function of x plus h minus function f of x whole divided by h equals limit h tends to 0, h times n times x to the power of n minus 1 plus 1/2 n times n1 times x to the power of n minus 2 times h plus h to the power of n minus 1 divided by h equals limit h tends to 0, n times x to the power of n minus 1 plus 1/2 n times n1 times x to the power of n minus 2 times h plus h to the power of n minus 1. Note here, h is not equals 0. The limit of the gradient, as h tends to 0, is n times x to the power of n minus 1. Terms containing h will be equals 0. Therefore, derivative f dashed x to the power of n equals d dx. X to the power of n equals n times x to the power of n minus 1. Derivative of 1 divided by x. Let's take another function. f x equals y equals 1 divided by x. Evaluating function of x plus h minus function f of x. That is 1 divided by x plus h minus 1 divided by x. Or solving the fraction by LCM method. Equals x minus h divided by x times x plus h. Equals minus h divided by x times x plus h. F dash of x equals dy dx equals limit h tends to 0, function of x plus h minus function f of x whole divided by h. Equals limit h tends to 0, minus h divided by x times x plus h whole divided by h. Equals limit h tends to 0, minus 1 divided by x times x plus h whole divided by h. Note here, h is not equals 0. The limit of the gradient as h0 is minus 1 or x2, terms containing h are equals 0. Therefore derivative d dx 1 divided by x equals minus 1 divided by x squared. Derivative of 1 divided by square root of x. Let's take another function f x equals y equals 1 divided by square root of x. Evaluating function of x plus h minus function f of x. That is 1 divided by square root of x plus h minus 1 divided by square root of x. Or solving the fraction by LCM method. Equals square root of x minus square root of x plus h. Whole divided by square root of x times square root of x plus h. To solve, we need to multiply by square root of x plus square root of x plus h. Function of x plus h minus function f of x. Equals square root of x minus square root of x plus h. Whole divided by square root of x times square root of x plus h. Times square root of x plus h whole divided by square root of x plus h. F dash of x equals dy dx equals limit h tends to 0. Function of x plus h minus function f of x. Whole divided by h. F dash of x equals dy dx equals limit h tends to 0, function of x plus h minus function f of x. Whole divided by h. Equals limit h tends to 0, in bracket minus h. Divided by square root of x times square root of x plus h times in bracket square root of x plus square root of x plus h. Whole divided by h. Equals limit h tends to 0. In bracket minus 1. Divided by square root of x times square root of x plus h times. In bracket square root of x plus square root of x plus h. Note here, h is not equals 0. The limit of the gradient as h0 is in bracket minus 1 divided by square root of x times square root of x times. In bracket square root of x plus square root of x. Equals minus 1 divided by 2x times square root of x. Terms containing h are equals 0. Therefore derivative d dx 1 divided by square root of x equals minus 1 divided by 2x times square root of x. power rule. For differentiation, finding the derivative from first principles can be tedious. The previous two examples clearly show this. However, using the first principles approach, we produced some results which are shown in the table. This power rule can also be written as: if y equals x to the power of n, then dy dx equals n times x to the power of n minus 1. Or if f x equals x to the power of n, then f dashed x to the power of n equals n times x to the power of n minus 1. Verify the power rule of x to the power of n. We have noted that derivative f dashed x to the power of n equals d dx x to the power of n equals n times x to the power of n minus 1. To avoid duplication and confusion, we will try to use notation of derivative as d dx. Note the derivative of x to the power of n, or d dx x to the power of n equals n times x to the power of n minus 1 is true for all values of n, and may be used as general rule. Let's check it. For n equals 3, y equals x cubed. Therefore d dx x cubed equals 3 times x to the power of 3 minus 1 equals 3 times x squared. And for n equals minus 2, y equals x to the power of minus 2. Therefore d dx x to the power of minus 2 equals minus 2 times x to the power of minus 3. And for n equals minus 3, y equals x to the power of minus 3. Therefore d dx x to the power of minus 3 equals minus 3 times x to the power of minus 4. General rules of derivative. Some general rule of derivatives we have proved. Number 1. Constant function f of constant c, or y equals c, therefore dy dx equals 0. 2. Y equals bx, therefore dy dx equals d dx bx equals b times d dx x equals b times 1 equals b. 3. Constant out f dashed of a times x squared equals d dx a times x squared equals a times 2x. 4. Plus rule y equals u plus v equals dy dx equals du dx plus dv dx. 5. F dashed of x cubed dx cubed dx equals 3 times x squared. 6. F dashed of x to the power of 4 dx to the power of 4 dx equals 4 times x cubed. 7. F dashed x to the power of n dx to the power of n dx equals n times x to the power of n minus 1. Tips to find derivative. Example: differentiate the function y equals square root of x plus 5 divided by 3x plus x. Before we differentiate the function, number 1, write it in the form of x to the power of n to apply power rule. Number 2, break the function in parts to make use of plus rule, that is d dx u plus v equals d dx u plus d dx v. Y equals square root of x plus 5 divided by 3x plus x equals x 1/2 plus 5 divided by 3 times x to the power of minus 1 plus x. D dx, x to the power of 1/2 plus 5 divided by 3 times x to the power of minus 1 plus x equals d dx, x to the power of 1/2 plus d dx, 5 divided by 3 times x to the power of minus 1 plus d dx, x equals 1/2 x to the power of minus 1/2 plus 5 divided by 3 times x to the power of minus 2 plus 1. Find the derivative. Example: differentiate the function f equals y equals x to the power of 4 plus x to the power of 2 plus 5 divided by x to the power of 3. Before we differentiate the function, number 1, write it in the form of x to the power of n to apply power rule. Number 2, break the function in parts to make use of plus rule. Y equals x to the power of 4 plus x to the power of 2 plus 5 divided by x to the power of 3 equals x to the power of 4 plus x to the power of 2 plus 5 times x to the power of minus 3 d dx, x to the power of 4 plus x to the power of 2 plus 5 times x to the power of minus 3 equals d dx, x to the power of 4 plus d dx, x to the power of 2 plus d dx, 5 times x to the power of minus 3 equals for x to the power of 3 plus 2x, plus 5 times minus 3 times x to the power of minus 4 equals for x to the power of 3 plus 2x minus 15 times x to the power of minus 4. Example: differentiate the function y equals x cubed plus 2 whole squared. Before we differentiate the function, we expand the bracket so that we have each terms in the form of x to the power of n. To apply power rule, break the function in parts to make use of plus rule. Y equals x cubed plus 2 whole squared equals x to the power of 6 plus 4x to the power of 3 plus 4 d dx, x to the power of 6 plus d dx for x to the power of 3 plus d dx 4 equals 6x to the power of 5 plus 12x to the power of 3. Example: differentiate the function y equals square root of x times in bracket 7x to the power of 3 plus 2x to the power of 2 plus square root of x. Before we differentiate the function, we expand the bracket so that we have each terms in the form of x to the power of n. To apply power rule, also break the function in parts. Y equals square root of x times 7x to the power of 3 plus 2x to the power of 2 plus square root of x equals x to the power of 1/2 times 7x to the power of 3 plus 2x to the power of 2 plus x to the power of 1/2 equals 7x to the power of 3.5 plus 2x to the power of 2.5 plus x. Therefore d dx, 7x to the power of 7 divided by 2 plus 2x to the power of 5 divided by 2 plus x equals d dx, 7x to the power of 3.5 plus d dx, 2x to the power of 2.5 plus d dx, x equals 7 times 7 divided by 2, x to the power of 5 halves, plus 2 times 5 divided by 2, x to the power of 3 halves, plus 1, equals 49 divided by 2 times x to the power of 2 and a half, plus 5x to the power of 1 and a half plus 1. The product function dx u times v equals v dx u plus u dx v. Let u and v are function of x, so u dash of x equals du dx equals limit h tends to 0, function u of x plus h minus function u f of x whole divided by h, and v dash of x equals dv dx equals limit h tends to 0, function v of x plus h minus function v f of x whole divided by h. Now, f u times v equals d dx u times v equals limit h tend to 0, u x plus h v x plus h minus u x v x divided by h. To solve it further, we add and subtract a term u x times v x plus h. d dx u times v equals limit h tend to 0 inch u x plus h times v x plus h minus u x times v x plus h plus u x times v x plus h minus u x times v x divided by h. d dx u times v equals limit h tends to 0 v x plus h times u x plus h minus u x plus u x times v x plus h minus v x whole divided by h equals limit h tends to 0 v x plus h times u x plus h minus u x whole divided by h plus u x times v x plus h minus v x whole divided by h equals limit h tends to 0 v x plus h times du dx plus u x times dv dx. The limit, as h tends to 0, is, note the terms containing h, will be equals 0. Therefore derivative d dx u times v equals v x times du dx plus u x times dv dx. Find the derivative using the product rule. Example: differentiate the function y equals square root of x times in bracket 7x to the power of 3 plus 2x to the power of 2. This function is made up of the product of two simple function of x, or take it as y equals u times v, where u equals square root of x, and v equals 7x cubed plus 2x squared. Both u and v are function of x, so u dash of x equals du dx equals 1/2 x to the power of minus 1/2, and v dash of x equals dv dx equals 7 times 3x squared plus 2 times 2x equals 21 squared plus 4x. Example: differentiate the function y equals square root of x, 7 by 3 plus 2x 2. The product function d dx u times v equals v times d dx u plus u times d dx v. dy dx equals d dx u times v equals 7 by 3 plus 2x2 times 1/2 x to the power of minus 1/2 plus x to the power of 1/2 times 21x squared plus 4x. By putting the value of u and v and their derivative equals 7/2 x to the power of 2½ plus x to the power of 1½ plus 21x to the power of 2½ plus 4q to the power of 1½ equals 24½ times x to the power of 2½ plus 5x to the power of 1½ Therefore dy dx equals d dx u times v equals 24½ times x 2½ plus 5x 1½ Find the derivative using the product rule. Example: differentiate the function y equals x cubed plus 2x times x squared plus x minus 3. This function is made up of the product of two simple functions of x, or take it as y equals u times v. Let u equals x cubed plus 2x. Here is wrongly written as x 1/2. And v equals x squared plus x minus 3. Both u and v are function of x. So u dash of x equals du dx equals 3x squared plus 2. And v dash of x equals dv dx equals 2x plus 1. Find the derivative using the product rule. Example: differentiate the function y equals x cubed plus 2x times x squared plus x minus 3. Continue further. The product function d dx u times v equals v times d dx u plus u times d dx v. dy dx equals d dx u times v equals x squared plus x minus 3 times 3x squared plus 2 plus x cubed plus 2x times 2x plus 1. By putting the value of u and v and their derivative equals 3x to the power of 4 plus 3x cubed minus 9x squared plus 2x squared plus 2x minus 6 plus 2x to the power of 4 plus 4x squared plus x cubed plus 2x equals 5x to the power of 4 plus 4x cubed plus 11x squared plus 4x minus 6. Therefore dy dx equals d dx u times v equals 5x to the power of 4 plus 4x cubed plus 11x squared plus 4x minus 6. Quotient rule. d dx u divided by v equals v d dx u minus u d dx v divided by v squared. Let u and v are function of x, so u dash of x equals du dx equals limit h tends to 0, function u of x plus h minus function u f of x whole divided by h, and v dash of x equals dv dx equals limit h tends to 0, function v of x plus h minus function v f of x whole divided by h. Now f u divided by v equals d dx u divided by v equals limit h tends to 0 u x plus h divided by v x plus h u x divided by v x divided by h. Rewrite f u divided by v equals d o dx u divided by v equals limit h tends to 0, 1 divided by h in bracket function u of x plus h divided by function v of x plus h minus function u of x divided by function v of x. D dx u divided by v equals limit h tends to 0, 1 divided by h in bracket function u of x plus h times function v of x minus function u of x times function v of x plus h whole divided by v x plus h times v of x. Solve it further. In numerator we add and subtract a term function u of x times function v of x. D dx u divided by v equals limit h tends to 0, 1 divided by h in bracket u of x plus h times v of x minus u of x times v of x plus u of x times v of x minus u of x times v of x plus h whole divided by v of x plus h times v of x. Rewrite d dx u divided by v equals limit h tends to 0, 1 divided by h in bracket v of x times u of x plus h minus u of x plus u of x times v of x minus v of x plus h whole divided by v of x plus h times v of x equals limit h tends to 0 in bracket v x times 1 divided by h times u x times u of x plus h minus u of x minus u x times 1 divided by h times v of x plus h minus v of x whole divided by v x plus h times v x. Or d dx u divided by v equals limit h tends to 0, 1 divided by function v of x plus h times function v of x in bracket function v of x times du dx minus function u of x times dv dx. Here we replaced the value of du o dx and dv o dx in the expression. Therefore, as the limit as h tends to 0, all terms containing h will be equals 0. Therefore derivative d dx u divided by v equals 1 divided by function v of x times function v of x in bracket function v of x times du dx minus function u of x times dv dx. D dx u divided by v equals in bracket function v of x times du dx minus function u of x times dv dx whole divided by square of function v of x. It is known as quotient rule. Find the derivative using the quotient rule. Example: differentiate the function y equals x squared divided by x cubed plus x minus 1. The function is made up of two simple functions of x. Or take it as y equals u divided by v. Let u equals x squared and v equals x cubed plus x minus 1 are function of x, so u dashed x equals du dx equals 2x and v dashed x equals dv dx equals 3x squared plus 1. Continuing further, apply quotient rule. D or dx u divided by v equals vd or dx u minus u to dx v divided by v squared. Dy or dx equals d or dx u divided by v equals x cubed plus x minus 1 times 2x minus x squared times 3x squared plus 1 divided by x cubed plus x minus 1 squared. By replacing the value of do dx and dv dx in the expression equals 2x to the power of 4 plus 2x squared minus 2x minus 3x to the power of 4 plus x squared divided by x to the power of 3 plus x minus 1 squared equals minus x to the power of 4 plus x squared minus 2x divided by x cubed plus x minus 1 squared. Therefore dy dx equals d dx u divided by v equals minus x to the power of 4 plus x squared minus 2x divided by x cubed plus x minus 1 squared. Find the derivative using the quotient rule. Example: show that the differentiation of the function y equals x squared minus 1 divided by x minus 1 is equals 1. The function is made up of two simple functions of x, or take it as y equals u divided by v. Let u equals x squared minus 1 and v equals x minus 1 are function of x, so u dashed x equals du dx equals 2x and v dashed x equals dv dx equals 1. Continuing further, apply quotient rule. D dx u divided by v equals vd dx u minus u dx v divided by v squared. Dy dx equals d dx u divided by v equals x minus 1 times 2x plus x squared minus 1 times 1 divided by x minus 1 whole squared. By replacing the value of u and v and their derivative, do dx and dv dx in the expression equals 2x squared minus 2x minus x squared minus 1 divided by x minus 1 whole squared equals x squared minus 2x plus 1 divided by x minus 1 whole squared equals x minus 1 whole squared divided by x minus 1 squared equals 1. Therefore dy dx equals d dx u divided by v equals 1. Chain rule. Dy dx equals dy dt times dt dx. The chain rule. Dy dx equals dy dt times dt dx. We explain it by an example. Take a complex function f x, which can be expressed as subfunction of another function t x of x. For example, take a function f x equals y equals for x squared minus 3x whole cubed. Here either the derivative can be calculated by solving first algebra expression for x squared minus 3x whole cubed and apply derivative rules, or apply chain rule altogether to get the derivative. So try first by solving the expression as that of a plus b whole cubed. Y equals, for x squared minus 3x whole cubed equals 64x to the power of 6 minus 144x to the power of 5 plus 108x to the power of 4 minus 27x to the power of 3. Continuing further, y sad smiley 4x squared minus 3x whole cubed equals 64x to the power of 6 minus 144x to the power of 5 plus 108x to the power of 4 minus 27x to the power of 3. Therefore, dy dx sad smiley 64 by 6x to the power of 5 minus 144 by 5x to the power of 4 plus 108 by 4x to the power of 3 minus 27 by 3x squared equals 384x to the power of 5 minus 720x to the power of 4 plus 432x cubed minus 81x squared. Now apply chain rule dy dx equals dy dt times dt dx. The function f x equals y equals for x squared minus 3x to the power of 3. Let assume t x equals for x squared minus 3x. And then f x equals y equals t x cubed. T dashed x equals dt dx equals 8x minus 3. And f t equals y sad face t to the power of 3 and f t equals dy dt equals 3t squared. We apply chain rule dy dx equals dy dt times dt dx. Therefore derivative dy dx equals dy dt times dt dx equals 3t squared times 8x minus 3 equals 3 for x squared minus 3x squared times 8x minus 3 equals 3, 16 to the power of 4 minus 24x to the power of 3 plus 9x squared times 8x minus 3 equals 48x to the power of 4 minus 72x to the power of 3 plus 27x squared times 8x minus 3 equals 48x to the power of 4 times 8x minus 72x to the power of 3 times 8 times plus 27x squared times 8x minus 48x to the power of 4 times 3 plus 72x 3 times to the power of 3 minus 27x squared times 3. Solving it further carefully, we the derivative dy dx equals 384x to the power of 5 minus 720x to the power of 4 plus 432x to the power of 3 minus 81x squared. It is important to observe the function carefully before we start differentiating. If the function is pure algebraic function, it is better to simplify the function in the form such that each term in the expression is in the form of x to the power of n. In some case, you may need to apply product rule or quotient rule. Chain rule is very useful when the function has many part and mixture of algebraic term, trigonometry term, exponential terms, etc. Thank you very much for watching this video on derived function or derivative or differentiation or differential calculus. You can watch our earlier video on school mathematics by subscribing my channel. Thanks.